Hello, and welcome to today's WJE webinar. My name is Liz Pimper, and I'll be your moderator for this webinar, Advances in Ultra High Performance Concrete. During the next hour, WJE materials engineers John Lawler and Elizabeth Nadelman will provide an overview of UHPC, including its constituent materials, mixture proportioning, and production processes, focusing on key differences between UHPC and conventional and high-performance concretes, as well as on current and future uses of UHPC in architectural and structural applications. And now I will turn it over to John to get us started. John?
Hello, everybody. I'm John Lawler from WJE's Janney Technical Center Laboratories in Northbrook, Illinois. I'll be talking today with my colleague Elizabeth Nadelman, also here at WJE's lab. And obviously the topic of the discussion today is ultra high performance concrete, or UHPC. So we've had more than 300 people register for this webinar, and based on this registration, we recognize that we're talking to structural and materials engineers, construction managers, architects, and some other folks. Our goal is to provide something of interest for each of the people here in the audience. Overall, the intent of our discussion today is to provide you a sense of what UHPC is, how it's produced, and where it can be used effectively. To that end, when we finish this presentation, you should be able to describe characteristics of UHPC and compare those characteristics to conventional concrete. You should also have an understanding of current applications of UHPC and be able to discuss some of the future directions that the technology is headed in. So here's the outline of today's presentation. We'll start by talking about what UHPC is, then get into UHPC mixtures, proportioning, and development of those mixtures. We'll talk about production of UHPC, as well as some current UHPC applications, and then, as I said, some of the future of UHPC. The presentation may get a little technical at times, but I hope you stick it through to the end, because we'll come back to kind of summarize some ideas as to when and how UHPC can best be used for your individual work. All right, so before we get into UHPC, I want to take a step back and start with some of the basic concepts regarding the use of concrete. The intent of the first couple slides that we're going to share here is not to show you something that you already know, but really to kind of illustrate that UHPC is just a natural evolution in the use of concrete. So to start at the beginning, early last century, it was recognized that a low water cement ratio produces a dense concrete. And that greater density gives us higher strength and lower permeability, good things for concrete. But there's a consequence there, and the limitation is workability. If you don't have enough water, the concrete just doesn't flow. In the 1970s or so, through the introduction of water-reducing admixtures or superplasticizers, we were able to lower that water cement ratio and still get that flow. The density of the concrete was improved even further by the incorporation of silica fume, which largely became commercialized at about this time. The combination of the low water cement ratio and the silica fume allowed very high strength concretes to be achieved relatively easily. However, pretty quickly after some laboratory work looking at the combination of the low water cement ratio and silica fume, there was a recognition that, hey, maybe that wasn't as good as it might seem, because there was a greater risk of cracking, which ultimately would compromise the durability of the structure. So moving beyond that, what was developed was an understanding that using other supplementary cementitious materials like fly ash, you could balance some of the effects of the silica fume while still taking advantage of the benefits of the low water cement ratio. At about this time, the term high performance concrete was coined to distinguish this type of concrete from the high strength concrete that had been used previously, where kind of by definition, high performance concrete was specifically focused on a certain property, such as durability. So then the next step along this process is really the development of now ultra high performance concrete. What we're doing here is getting an ultra low water cement ratio, again through high dosages of superplasticizer. The elimination of coarse aggregate from the mix, as well as the introduction of supplemental materials, allowed for a focus on particle packing As we'll talk about a little bit more later in this presentation, the idea behind particle packing is to really maximize the density of our material, and there's performance benefits associated with that we'll get into. Another characteristic of the ultra high performance concrete is the introduction of fibers, and those introduce tensile properties that can be relied on. And again, I'll get into that a little bit more. So as you can see from our timeline here, ultra high performance concrete's been around since the 90s, but to date it's seen limited implementation, and that's largely because of a high cost, and also as a result of a lack of specifications and design guidelines. But that's starting to change, and again, we'll kind of come back to that as we go through this. So, kind of summarizing that, what is ultra high performance concrete? Well, it is a fiber reinforced cementitious composite with a low water cement ratio. But most of the materials that are incorporated in UHPC are the same as we use in conventional and high performance concretes. So we've got a cement, a supplemental cementitious material that can be silica fume as well as other materials. We've got a fine sand, fibers specifically tailored to the application, and then superplasticizer and water. So notice there are no coarse aggregates, since that can interfere with the function of the fibers and compromise the strength of the composite that we're going for here. And there's also no air entraining agent included in UHPC, and I'll get back to that, at least in most UHPCs, and I'll get back to that later also. So ultimately, how does it behave? Well, UHPC is characterized by an ultra-high compressive strength, but also high pre- and post-cracking tensile strengths. And then beyond that, there's due to the high density and discontinuous pore structure, we've got a significantly enhanced durability possible with this material. So the two types of performance that really make UHPC different from concretes that have been used historically are these last two, the tensile strength and the durability. I'm going to get into each one of those individually here. So what do I mean by tensile strength? Well, and how is UHPC different from conventional concrete? Well, first of all, UHPC is stronger in tension, which can actually be evaluated based on flexural testing, which is the basis of the curve that's being shown on the right of the screen here. But the concrete is stronger in tension to the point that the tensile capacity can be relied on in the design of structures. For conventional concretes, we discount tensile performance, but for UHPC, we can consider it. Beyond that initial strength, the material actually becomes stronger after it develops its first crack, because the high strength fibers bridge those cracks and carry those tensile forces across the crack. When you get more fibers mobilizing, that eventually will lead to the ultimate maximum load that concrete can carry in tension. But then even after we get those cracks, the fibers hold those cracks together, absorbing energy as the UHPC continues to deform. And the area under the curve represents that energy. The area under the curve in this kind of a plot. So you can see how much larger the blue area is, representing the UHPC toughness compared to the red, which is a conventional concrete. And here's an example of the tensile performance in action. This is a UHPC beam that was loaded to failure. And you can see along the crack that developed all the fine multiple cracks as the fibers mobilized the material. As I mentioned, the other important property that separates UHPC from other concretes is its durability. So here are some examples. You may be familiar with the Treat Island exposure site in Maine. This is a tidal area that's been used to evaluate all sorts of concrete over the years. But there were some samples of UHPC that were located there. The samples see 100 freeze-thaw cycles per year and tides of 20 feet. They were definitely seeing freeze-thaw cycles through 15 years or so, and there was really no degradation of the material over this period. And again, I mentioned earlier that we don't include air entrainment typically in UHPCs, but they do have this ability to resist the freeze-thaw distress as a result of its high strength and the low porosity that keeps the moisture from moving through the material. The other property that was evaluated in these UHPC mixtures at that Treat Island site was chloride ingress. Chlorides, as most folks are familiar with, I'm sure, are one of the main causes of corrosion of concrete. And so the more resistant to chloride ingress the concrete is, the more durability that can be achieved. So what's shown here in this figure are chloride profiles of a high performance concrete. Those are the blue lines. And compare it against the chloride profile, that is the amount of chloride penetrating through the depth of the concrete for UHPCs. That's the orange and gray line. And so what you can see is even for that high performance concrete, which was a pretty durable mix in and of itself, a water cement ratio of 0.33 and still 8% silica fume, over that time period, chlorides were able to penetrate to a depth of about 20 millimeters. In a similar duration, the gray line there, you can see that very little chloride is penetrated past about 7 millimeters. So let me take a step back then and compare typical properties of conventional concrete and ultra high performance concrete. First of all, the compressive strength. For UHPCs, the strengths that we're looking at are generally more than 17,000 PSI. Some definitions set that limit as over 21,000, and values up to 25,000 PSI have certainly been achieved. What that means is that structural elements that are loaded in compression can be significantly thinner and carry just as much load as conventional concrete. Tensile strength of UHPC, as I mentioned earlier, is something that can be relied on for design in UHPC, where generally for conventional concrete, we just discount it. And what that means is that reinforcing steel can potentially be reduced or eliminated because the material itself is able to carry some of the tensile loads. All right, so those are two areas where UHPC is significantly better than conventional concrete. Shrinkage is an area where actually the performance of UHPC is perhaps not favorable compared to conventional concrete. And really, a primary contributor of cracking in concrete structure is shrinkage if that shrinkage is restrained. One of the side effects of eliminating the aggregate and reducing the water cement ratio in the UHPC is a greater tendency for that concrete to shrink compared to conventional concrete. However, since most of the shrinkage in the UHPC occurs at early ages, in some settings, especially, for example, precast concrete, that can be accounted for in design, and so perhaps doesn't have the negative consequences as one might fear. All right, from a durability perspective, I talked about chloride ingress a little bit before. The chloride diffusion coefficient is a testable, quantifiable value for how well that concrete resists the ingress of chlorides. And what you can see by looking at these numbers is the chloride diffusion coefficient of UHPC is about 2 orders of magnitude greater than, smaller than conventional concrete, which basically means there's about 100 times greater resistance to chloride ingress with UHPC, obviously beneficial from a durability perspective. Testing the freeze-thaw resistance of UHPC, what we see is that the relative dynamic modulus after 300 cycles in the ASTM C666 test procedure, which is basically a rapid freezing and thawing cycling procedure, we get very little degradation of the UHPC. A perfect performance in that test would be 100%, and generally what we get with UHPC is 95% or better. Compare that against conventional concrete, where after a similar number of cycles, we're generally seeing about 75%, meaning there was significant degradation experienced by the material. So far I've been talking about UHPC as if it's just one thing, but UHPC is really a class of materials that comes in a number of different varieties. These can really be grouped into prepackaged materials and local material-based mixtures. So an obvious example of a prepackaged material is ductile. That's a material that has been commercialized by Lafarge. Essentially what that is a set of materials that have been pre-selected and combined before they're shipped out to the job site. The advantages of this approach is that the supplier providing the prepackaged mixture can be more selective in the choice of the raw materials that they use. and there's a certain level of consistency in the batching process that can be assumed. Another benefit of the prepackaged material is that there is a reduced batch time associated with their use. One of the disadvantages of the prepackaged materials is their high cost. And so this is one of the reasons that there's been interest in recent years, especially in looking at locally sourced materials for use in UHPC. An advantage of the local material-based mixtures is that the materials can be selected to be conducive to production based on the local process, but they can also be tailored to the specific project needs. For example, depending on the design and the use of the materials, you might not need a particularly high compressive strength, and you can focus on, say, 18,000 PSI compressive strength is sufficient for your needs. But one of the consequences of the use of local materials is, one, obviously you've got to have a certain level of local expertise in order to produce the material successfully. And then in addition, because it is a new mix design, logically there's a greater amount of verification testing that's needed before it can be applied. Whereas with the prepackaged materials, there's a certain level of confidence on how that material is going to perform. With local materials, that performance really needs to be verified. And I should say again, the local material-based kind of approach is something that is growing in interest around the country. And WJE has actually been part of a number of projects where we've worked with individual groups, precasters especially, looking to develop mixes based on their local materials. With that, I'll turn it over to Elizabeth to talk a little bit about UHPC mixtures.
All right, thank you, John. So John talked a lot about the specific performance characteristics of UHPC, the high compressive strength, the post-cracking tensile strength and ductility, and the high durability. So we're going to dive in a little bit deeper and talk about where does that performance come from. One thing that obviously is going to contribute to some of that high performance is the ultra-low water to cement ratio of the UHPC. As John mentioned previously, UHPC is typically batched at water to cement ratios of 0.2 or less, which is even off the chart that I'm showing here in this figure. Naturally, at those low water contents, you're going to see significant benefits in terms of material performance and compressive strength in particular. It also comes from the use of supplementary cementitious materials, or SCMs, in particular silica fume, which is a very fast reacting material. The silica fume and other SCMs that are present can produce additional hydration products that make the concrete denser, make it stronger, make it more durable. As John alluded to as well, the fibers are going to contribute significantly, in particular to the ductility and post-cracking strength of the material. But really what comes down to is the performance of UHPC is going to be based largely on an optimized packing of particles. We're talking about making the material as dense as possible, and so we need to be able to fit particles together from all different size ranges, with the aggregates, the fine aggregates being some of the coarsest materials in the system, all the way down to silica fume being the smallest material in the system. When you have that dense packing that comes from having this optimized gradation of particles, not only do you get high strength and high durability, but surprisingly, you also get high workability. And that's because if you look at this figure I'm showing here on the right, when you have a lot of particles together, you don't have as much water that gets trapped in between them. That water is freed up to help lubricate those particles. So you actually see a little bit of benefit with respect to workability or flow properties as well. So we're going to talk a little bit more specifically now about some of the materials that go into UHPC. Again, these are very similar to the materials that you'll see in conventional concrete, but there might be a little bit, a few differences here and there. So typically UHPC is going to consist of a Portland cement. We, at least at WJE, have worked with UHPC mixtures that contain type 1 cements, type 2 cements, type 3 cements, even white cements. So there's a lot of different cements that can be used successfully in UHPC. Primarily, it's going to have silica fume. Almost every UHPC mixture currently being developed has silica fume, though there are a few exceptions. The silica fume is really important because it's going to be the finest material in that system. And so if you're trying to get a very dense system, you need to have a very fine material that can fit in and fill those pockets between the particles. It'll also contain a supplemental material. And notice I'm not calling this a supplemental cementitious material, but a supplemental material because it doesn't have to be reactive. Some of these materials might include a silica flour, which is a non-reactive material, or it may include a fly ash, which is reactive. The purpose of this material is going to be to facilitate that particle packing, not so much that it's going to react to form hydration products. The UHPC will also consist of a fine sand, no coarse aggregates. It'll have those fibers. Fibers will typically be steel fibers if you're using them in a structural application, but they can also be polymeric fibers if you're using them, for example, in an architectural application where the appearance might be important. You don't necessarily want to see small little corrosion spots where the steel fibers are very near to the surface. So there are different fibers that may be used. And also certain polymeric fibers can provide fire resistance as well. And finally, the UHPC is going to consist of superplasticizer. These are typically polycarboxylate materials. So these are very efficient superplasticizers for materials that contain high volumes of powder material. And you'll use them at several times the dosage that you might actually see in conventional concrete. What this superplasticizer does is it facilitates some of the workability properties of the UHPC and makes it a very flowable material, even though it has a very low water content. And as John mentioned before, these materials can be prepackaged or they can come from local sources. And so there's going to be some differences in the consistency of the materials that may be present if you have a prepackaged UHPC versus a local sourced UHPC. When it comes to proportioning UHPC, there's no unique mix design. I can't just pull a mix off the shelf and say this is going to be a UHPC. It might not even work. And the rule of thumb guidance doesn't apply. And the reason for this is because, as I mentioned before, the performance of the UHPC is dependent both on the chemistry of the material, so the cement's chemistry, the chemistry of maybe a fly ash that's in the material, as well as the gradation of the particles. And if I change one of those materials out for an alternative, maybe I substitute a sand of one gradation for a sand of a slightly different gradation, my mixture proportions will actually have to change quite a bit if those particle sizes change to account for the difference in particle packing with those new systems. So I'm going to show an example of a UHPC mixture right here. These are proportions by weight. On the left is a conventional concrete, and you can see it's got cement, water, fine aggregate, and coarse aggregate. This is at about a 0.5 water cement ratio. And it contains roughly 600 pounds per cubic yard of cement. So this is what would be called a 6-sack mix, which means it has 6 sacks contains 6 94-pound sacks of cement. On the right is a UHPC mixture, loosely based on the proportions of ductile, though not entirely the same. And what you can see is that the total amount of cementitious material in these mixtures is actually quite different. On the left, in the conventional concrete, the cementitious materials make up about 15% of the material's weight. In the UHPC, it's closer to 45%. So a lot more cementitious content in this mixture. Otherwise, the material proportions are actually fairly similar with respect to the water, which is about 7% in both mixes. The aggregates, the fine aggregates, which are about 35 to 40% for both mixtures. Effectively, what the main difference in proportions is where the conventional concrete is going to have coarse aggregate, that entire weight is substituted with fibers and additional cementitious material. So I mentioned that this conventional concrete mixture might be what's considered a 6-sack mix. If I did the same math for a UHPC mixture, it would be a 20 sac mix. So now I'm just going to show the numbers that are associated with those graphs. I know some of you are probably more number people and others are graph people. So just to compare the numbers a little bit, the conventional concrete has 600 pounds of cementitious material. That UHPC mixture, by comparison, has over 1,900 pounds of cementitious material. And then that water to cement ratio or water to binder ratio that I'm showing, because there's so much cementitious material in this mixture, our water to binder ratio is going to be less than 0.2. So now let's talk a little bit more specifically about how we actually develop these UHPC mixtures, with particular attention to local materials, since that's what John and I have worked with quite a bit lately. So there's a few different approaches to developing UHPC mixtures. One is to do sequential trials. So what this would be is, say I've developed a mix design on paper and I test it out in my plant or in the lab, and I see, is the workability where I want it to be? If it's not, well, maybe I want to change the proportions of my sand, maybe reduce some sand, add some cement, add a little bit more water, change my super plasticizer. Essentially, batch a mix, see how it performs, make a few iterative adjustments, and then batch again until we get a mixture that performs the way you're looking for. There's also experimental design methods where if I'm looking at a particular group of cements, particular group of supplemental materials, maybe a few different sand gradations, I look at different options from each of those categories and use statistical principles to come up with a matrix of different mixtures that I'm going to make. I make all of the mixtures, evaluate their performance, and then use statistics to figure out, based on the performance of each of those mixtures, which component at which dosage is going to give me the best performance. The third approach, which is one that John and I have used quite a bit recently and found to be very effective, is to use particle packing models. And since this is unfamiliar to most of you, I'm going to do a very, very broad overview of what a particle packing might look like. So one of the particle packing models that John and I have used is called the modified Andreessen and Anderson model. And basically what it does is it looks at the gradations of the different materials. So many of you are probably familiar with a gradation for sand, which I'm showing here on this graph. So what a gradation is going to do is it's going to say for a given size range, I have a certain percentage of my material that falls into that size range. Well, we can get the same information for our cements and our silica fumes and for other powder materials as well. Then when we combine those materials in certain ratios, we'll get a combined gradation that represents all of the sizes in that combination of the materials, all the way from the finest material, which is probably going to be mostly the silica fume, up to the coarsest material, which is going to be mostly the sand. Once we have our combined gradation, we're going to look for a target gradation that's going to be defined by our particle packing model. What we're trying to do is adjust those proportions so that our combined material is as close to the target as we can get. So for this example, I have a little bit more coarse material than I want. So maybe I'll reduce the amount of sand that I have in this combination and increase the silica fume. Maybe I'll get this combination. Well, this one now is a little bit too fine, so I'll adjust again. And now I'm very close to that curve. These proportions are going to be close to what I want to work with. And so then I'll play around in the lab or in the plant and try different water combinations, different admixture combinations till I get the performance characteristics I'm looking for. So when I'm developing a mix, here's a few of the performance characteristics I might consider. Obviously, the compressive and tensile strength, the durability that we've talked about, the long-term material availability. Do I have a particular material that I'm concerned isn't going to be available for the duration of a particular project I'm working on? That's a factor that might be considered. Workability and workability retention. How flowable is this material? Does it have self-consolidating properties? And how long does it stay self-consolidating? How expensive is the mix going to be? What's the cost? And also, what are the production capabilities at the plant? Do I have enough silos at the plant to handle an additional supplemental material, for example? So just to give you an example, if I'm developing a mix design, I might consider the ones I've highlighted first. I might consider compressive strength, workability, cost, and production capabilities to make my initial selection. But once I've developed a mixture that I'm happy with that meets those 4 criteria satisfactorily, then I'll look at the other ones and do additional evaluations to make sure that my mix is going to work long term. In terms of characterizing the UHPC performance, I did talk about workability and workability retention, and this picture is performing a flow test. So UHPC is self-consolidating. It'll flow under its own weight. And we perform a flow spread test that's very similar to what's done maybe with self-consolidating concrete, except it's done with this small little 4-inch cone, so it's a much smaller scale test. We can also measure the temperature of the UHPC. John will talk later on about how temperature is very important when it comes to long-term workability. So temperature is very important. And also setting time, which is good to know for a lot of production applications. In terms of mechanical properties, we can characterize the compressive strength and elastic modulus of the concrete. We can characterize the flexural and tensile performance of the UHPC. This is a picture of a flexural test that we've performed in our lab recently. And then we can also characterize the creep and shrinkage performance of the mixture. These are properties that are going to be very important when it comes to design with UHPC. And WJE is now accredited to perform all of these tests under ASTM C1856, which is a new standard that defines testing procedures for ultra-high performance concrete. And finally, when I think of ultra-high performance, I think of performance, I think of durability. And so for UHPC, it's often also important to characterize the durability. And so this can be accomplished through characterizing the absorption, which reflects how much moisture can be absorbed by the concrete. It can be performed by assessing the chloride penetrability, either through a rapid chloride permeability test or RCP test, which a lot of DOTs specify, or it can be accomplished through a diffusion coefficient test, which is probably a little bit more accurate for a material like this that's got a pretty high density. And finally, you can characterize the freeze-thaw resistance, which I'm showing in this figure here.
All right, so I'm going to come back in now and talk a little bit about the production of UHPC. UHPC can be produced generally using similar equipment, same forms, for example, as conventional concrete, but there are some additional areas that need to be considered. Obviously, materials acquisition and handling may be a little bit different if we are talking about different raw materials than conventional concrete. The charging sequence of the mixer, especially handling the fibers, is something that's a little different. Batching controls, 2 important components for conventional concrete that are even more important for ultra high performance concrete, are moisture and temperature, and then placing, finishing, curing